In this clip, I will go over what I covered at the start of lecture 2, which was not recorded due to an issue with the podcast. So at the start of lecture 2, I first went over the properties of MA processes. I'm also going to cover this in the recap session this Friday. Okay, so remember, the MA1 process, one of the simplest processes we've seen, is just a function of a constant, alpha, plus the shock at time t. You can think of this as the shock at time t, and the shock at time t minus 1. Whereas throughout, we're assuming that epsilon t is white noise, which means, remember, that the mean is not, just an assumption that the variance is not, and because, the variance is constant and finite. And again, remember, because the mean is not, then this is the variance, and that the covariance in different time periods is not, that they're uncorrelated. Okay, and we maintain, whichever model we use, we always assume that the errors are white noise. The idea being that we specified all the dynamics in the model such that everything that's left at time t is just some random white noise shock. Okay? So, what then are the properties of yt if yt is an MA1 process? Well, we just plug in yt into here to work out the sample average. Again, the expectation of the sum is the sum of the averages, is the average of the sum. So we're going to get, again, expand it all out. And we use the fact that by white noise, both of these equal naught, so we get equals alpha. And again, it's crucial in the exam that you give detail in your steps. So you say how you get from one step to the next. Okay, so the simplest way to lose mark in an exam would be to go from, say, this step to here to alpha, but not say that it's by the white noise assumption, it's by this assumption here that the mean is not due to white noise. Okay, so then we move on to the variance. Well, the variance of yt, well, remember first, the general formula is the average value of yt minus the mean squared. By the above, we've seen that this term here equals alpha, which gets us to this step. Then we just plug in from above. Yt minus alpha is just a shock at epsilon t plus the e1, the shock at epsilon t minus 1. Then expand it all out, and we're going to expand the quadratic. We're going to get e of epsilon t squared plus psi1 squared e of this squared, and again 2 times theta 1 of the average of the shock in each period. Okay, so expanding out the quadratic and taking expectations, then we can see that by white noise, this term here equals sigma squared, this term here equals sigma squared, and this term here equals naught, by using these 3 assumptions of white noise. Putting it all together, we get the variance of yt is sigma squared 1 plus psi1 squared. Okay, so using the white noise assumption, we've shown that the mean of this process is alpha, and the variance of this process is sigma squared 1 plus psi1 squared. Okay, the next crucial thing to look at then is what is the covariance function of an MA1 process. So remember, for a covariance function, we need to derive the covariance at yt with all past legs, not just 1 or 2 of the legs, but all of them. So first off, the covariance of yt and yt minus 1. Often we use this shorthand as gamma 1. First off, this is just the definition of the covariance of yt and yt minus 1. We then, next line, use the fact that the average in any time period of yt is alpha from before. We then plug in yt minus alpha and then recurse it back one period, we get yt minus 1 minus alpha. Okay, then expand it all out, we're going to get 4 terms. When inside the bracket, when we multiply these 2 terms by these 2 terms, we expand it out, we're going to get 1, 2, 3, 4 terms. And again, you can see all of the terms which are products in different time periods, when we expand out, will all have mean naught by the white noise assumption that E of epsilon t, epsilon s equals naught in different time periods. The only non-zero term that will come out is this term here, and again by white noise, this variance equals sigma squared. So again, we've used the white noise here repeatedly. We can then do the exact same thing again. Again, I've skipped steps here, but we can use a formula above. This is yt minus alpha This is yt minus 2 minus alpha. We can see when we expand out, all cross product terms are going to be in different time periods. Therefore, it will equal naught by white noise. And again, this is true for any lag. So this just says the covariance of yt, and yt j periods back. For any j greater or equal to 2 will always equal naught. And again, it makes sense. Looking at the white noise, looking at the MA process, it says yt is a function of the shock now, and the shock at time t minus 1 multiplied by this coefficient theta 1. If theta 1 is positive, we're going to get a positive covariance, a positive correlation between yt and yt minus 1. And the reverse if theta 1 is less than 1. We can see that yt doesn't depend on the shock from t minus 2 or before. Therefore, because all the shocks are uncorrelated, yt, by construction here, can only be correlated with yt minus 1 and nowhere else. Okay, so everything makes sense here. We can generalize all these results to the case of an MAQ process. An MAQ just generalizes from before to have a process which is a function of up to q lags into the past of the shock, where these coefficients on the shock give show how the shock from that period, so many periods back, affects yt into the future. And again, we can derive the mean, plug this into here, we find this. We can derive the variance. Again, the variance of yt is going to be the variance of all these terms, and the variance of the sum is the sum of all the variances, because epsilon t is uncorrelated. And again, we're going to show this in the support hours. So I'm going to skip this for the details. It's in the notes to lecture 1. But again, you can see intuitively this is just the sum of all the variances of all these terms here. Again, because all of the covariances are naught. And finally then, the trickier part is to derive the covariance function. For any j, then we can show that the covariance function looks like this, where we always set theta naught equal 1. Okay, so we're going to show, the lecture notes go through this in some detail. I've had a few people ask about this. I think it's best to go over this in the support hour on Friday, and if people still have questions, I can make another video clip about this. Okay. So we just quickly then recapped how to derive the properties of an MA1 and seeing the properties of an MAQ process, and we're going to go into that in more detail on Friday this week. We then went on and started lecture 2 then. Again, we recapped the lectures, we then defined an MA infinity process. An MA infinity is just an MAQ model where we let the number of lags q go off to infinity. So by definition, yt, if it's MA infinity, is equal to a constant, plus the weighted sum of all the shocks from the past, like 1, like 2, like 3, back forever, where theta j are these weights. It's the effect of epsilon t, j periods back on that. Okay? So again, you can see this is a very flexible model. It's a function of all the lags into the past. As we vary these coefficients, we can allow these theta, we can allow different forms of correlation patterns. Okay, and we can see, and again, we can just use the results from before. So we literally, in the MA infinity slide, we use all these results and let q go off to infinity. So again, this here will tend toward sigma squared sum j equals 0 to infinity of theta j squared. Remember, we set theta naught equal 1. Again, if the limit exists, if this is finite, again, the sum of an infinite number of coefficients may not be finite. And if it wasn't the case, then the limit wouldn't exist. So for example, we can't have theta j equal 1 for all j. Otherwise, the limit would be infinite. Okay, so normally these coefficients, as j gets bigger and bigger, have to be declining very quickly, such that the sum of them is still finite. And again, we can also find the covariance function by letting the q go off to infinity. Okay, so to get the properties of an MA infinity is relatively straightforward. We just use result from before, where now q goes off to infinity, and we have to assume that these are finite here. Okay. And just to be clear, if this is finite, it implies this term is finite as well. So we don't need to prove this, but again, if the variance is finite, we can show the covariance has to be finite as well. So once we derive the properties of an MAQ, we already have the properties of the MA infinity. Let Q go off to infinity and assume the sum of these squared coefficients is finite. Okay, so this is the squared summability condition, that the sum of these coefficients here in the variant is finite. Otherwise, the variance won't exist. Okay. So the only condition we need for stationarity in an MA infinity, we've shown that it's got constant mean, we've shown it's got constant variance, and the covariance function just depends on the gap, doesn't depend upon t. The only thing left is we've got to have finite variance, which is from the squared summability. So again, a general result, an MA infinity is stationary if the sum of the coefficients squared is finite, which is known as squared summability. And what we can show is sometimes a question may ask you to derive to show that the coefficients are absolutely summable, which means that the sum of the absolute coefficients is less than infinity. And we can show that absolute summability implies squared summability. So we can either directly show that the sum of the coefficients squared is finite, or we can show that the sum of the absolute coefficients is finite, because this absolute summability implies squared summability, which implies stationarity. Okay? So why is this useful then? Well, what we can show is that any stationary process can be sorry, this should be capital YT, remember we use capital Y to mean the random variable. Then, the theorem by Wall, which we don't need to prove, is that any stationary process can be expressed as an MA infinity process. And it also makes sense, because this states that YT is any linear combination of all the shocks into the past. So this MA infinity model allows extremely complex and differing types of correlation with the past, and this is why we get the result. So this MA infinity can essentially approximate any stationary model. Okay, so we can use that then to derive the properties of an MA of an AR1. So we're going to assume stationarity, which here means the absolute value of phi1 is less than 1. Okay, so again we have the AR1 here. Assuming stationarity, then we know by the Wald theorem that we can write YT as some MA infinity process. And we find this by back recursing. So this is a very common method used when deriving the properties of AR models. Okay, we need to work out YT minus 1. Well, this equation holds for all time periods. So it also holds at YT minus 1. Therefore, YT minus 1 equals mu plus psi YT minus 2 plus epsilon T minus 1. We can plug this term into here and expand it out, which we get to this line here. We could do the exact same for YT minus 2, recurse it back one period, plug this into here, and we expand out. And if we keep going back, so we can see we've gone back 2 periods here, and we can see what happens. We've summed up to mu phi1 squared. We've gone back to 3 here, which is j plus 1. And we've gone back to the sum of, see how the coefficients, see how the lag matches the coefficient. This is phi1 to the 1. The lag here matches the power here. Okay, so if you can do it yourself by hand. If we now worked out YT minus 3 and went back and kept going, if we did this j period, well, we're going to get the sum of this up to j, okay, and which we saw here for j equals 2. So this just generalizes it to, j equal 3, 4, 5, 6. Again, if we go back j periods then, well, we're going to get j to the power plus 1. We get this here, minus this. And again, we did this for j equal 2. So j plus 1 equals 3, j plus 1 equals 3. And again, we sum back, weighted sum back j times. We go epsilon t, we go back, this is to j minus 1. So again, we're going to get minus j minus 1 here, so we're going to probably get the plus 1 back to j, and again we did it for j equals 2 here, so again it also matches, we can see it also matches here, doing it for the general j. So we just, again, if you're not clear on that, do it for j equals 3, j equals 4, this is a general pattern. No matter which j we do it for, 3, 4, 5, 6, this is what it will look like. And what we do is we let j go off to infinity, and if phi1 is less than 1 in absolute value, then this term here declines exponentially quickly. So this tends towards not exponentially fast when it's less than 1 in absolute value, which we've maintained, which gives us stationarity, which is why the effect of the past dies away. Therefore, what we're left with then is just this sum as j goes off to infinity, which we can just re-express here. Okay, this is for general j. If we let j go off to infinity, it goes back forever. This is just this sum. And again, also note that this here is a geometric progression in phi1. And again, so if we let j go off to infinity, we're going to get mu over 1 minus phi1. Okay, so see the lecture notes on this for the details on the geometric progression. But the idea is we keep back substituting again and again and again. If phi1 is less than 1 in absolute value, the effect of the past dies away. We've now written the AR1, the stationary AR1, into its MA infinity form, where the alpha coefficient is mu over 1 minus phi1. And we can see that the coefficient phi here is just phi1 to the s. Okay, so using from before, we now have an MA infinity process where the constant is mu over 1 minus phi1, and the coefficient any lag, s, is just phi1 to the power s. So we have now the MA infinity form of a stationary AR1. Once we have this, then we can use the general formulas for the mean, the variance, and the covariance of an MA infinity process. Okay? So when phi1 is less than 1, just to be clear, these two are equal to each other. So this is equivalent, this means equivalent to yt equal this. The two things are the same. We want the variance of this. Well, because we just re-expressed it as this, well, we can just find the variance and the mean and the covariance of this. And this is just an MA infinity model with some particular coefficients. Okay, so this is why these MA infinity results are very useful for deriving general properties. Okay, so this is what we just saw on the last slide. When phi1 is less than 1, we can write the AR1 equivalently in its MA infinity form. So straight away then, we know that the mean of yt is equal to alpha, which is, so this should be a mu here, sorry, which is then here, this is just the alpha from before. Okay, we now have the variance, which is sigma squared, the sum of all these theta squared. Well, theta s just equals phi1 to the s. Plug this in, we're going to get 1 plus phi1 squared plus phi1 to the 4. This is just a geometric progression in phi1 squared now. Okay, so therefore the limit when phi1 is less than 1 is 1 over 1 minus phi1 squared. So again, we've just used a general formula for the variance of an MA infinity for some particular coefficients and used the fact that phi1 is less than 1. We can see that, of course, if phi1 equaled 1, this will be infinite. So that's why we have to have that phi1 is less than 1. We can also use a general formula for the covariance of an MA infinity at lag yt and yt minus k. So remember, this is just shorthand notation for covariance of yt minus k. Again, general formula, just plug in theta s is phi1 to the s. And of course, phi s to the k is phi1 to the s plus k. Plug it in. The powers add up. We're going to get equals sigma squared phi1 2s plus k. We can take phi1 to the k out. So again, remember, we can write this as phi1 2s dot phi1 to the k. We could take the k outside because the sum doesn't depend upon k. And this here is just a geometric progression in phi1 squared. We can see this term here is just the variance of yt we derived before, which we write shorthand as gamma naught. Okay, so this then is the covariance between yt and yt minus k, then we're done then. We can get the correlation function, because remember, the correlation is the covariance of yt minus k divided by the variance of yt, which shorthand is just gamma k over gamma naught. So here we do it very simply then, we have phi1 to the k. So this, the AR1 coefficient to the power k gives us the correlation of yt with ytk periods back. If phi1 is less than naught, the correlation is always positive and it's quickly decreasing in k, which makes sense because the effect of the pass is dying away. And if phi1 is less than 1, then we're going to get an oscillating pattern. If k is odd, we're going to get a negative correlation, and if k is positive, if k is even, we get a positive correlation. There's an oscillating relationship with the past. Okay, and this just plots this here. So take an example where phi1 is greater than naught. So this is just one example of the case phi1 equals 9. This just plots on the graph phi1 to the k against the lag. We can see that it declined exponentially quickly. This here is an example where phi1 is less than 1, you have minus 0.5. Then we're going to get oscillating. It's going to go from negative, positive, and dampen out. Okay, so because it's stationary, the correlations are tending towards naught. They get smaller. And of course, the bigger the coefficient, the slower that they go towards naught. Okay, so we've used the MA infinity representation of the stationary AR1 to derive the mean, the variance, and the covariance. Okay, this is about as far as I got, I think. So we'll leave it there, and we will go over the MA infinity model in the support hours this Friday coming, November the 4th.